Welcome to Wireless Future. I'm Erik Larsson, and I'm here as always with my colleague Emil Björnsson. Today we have a guest, Bengt Lindoff. Bengt has his PhD in math and worked for many years at Ericsson Research, where he also was named Inventor of the Year. And more recently is heading the new startup company Beamwave that focuses on technical solutions for fully digital millimeter wave. And Emil, we have been preaching, I think, fully digital beamforming for massive MIMO for something like 10 years now.
Yeah.
And for lower frequency bands, this is kind of the obvious solution. But it's also exciting to see that technological solutions now are emerging also for the millimeter wave band. So, Bengt, would you like to tell us a little bit about your company and the architecture that you are developing?
Yes, thank you, Erik. I'm working as a chief system architect for Beamwave, which is a startup company in Lund, Sweden. And it was founded 4 years ago by the founders, which was Marcus Terminen, who is professor in RF design in Lund University, and Per-Olof Brandt. He is a senior radio RF designer, been working for various companies with RF design for more than 20 years. So they started with some research project, I guess it was a year before they started the company, 2014-15, about thinking about when people thought about this massive MIMO and beamforming, and we are coming up to millimeter wave. How should you do the radio design if you start from scratch, so that you don't think about all the legacy you have and see, okay, how should you do it in a good way that you can a scalable solution, basically, where if you go to the millimeter wave, we know that the antennas, they go down to some few millimeters, meaning that you can basically integrate them in the chip, and then you can integrate the antennas and the front-end modules and the radio in the same chip or in the same encapsulation. And then, in order to have a scalable solution, say that if you have some few transceivers for some devices, but other devices maybe needs tens or hundreds, can you do some kind of scaling with the same kind of components? And then they end up in that basically the digital beamforming is the solution to that kind of system, and looking at the state of the art in radio, it turns out that it's now you have the possibility to do all this kind of thing. So they started this company after the research and made some patents, and currently we are designing our first radio chip for millimeter wave, focusing on 5G. The frequencies for 5G, which is today 28 and 39, but of course there will be more frequency bands in the millimeter wave in the future. We are the company is focusing on the radio part, so we are not doing the baseband or the decoding or all that kind of stuff. So we need to partner or sell our chip to baseband together with some baseband partners to integrate it in mainly handheld devices or other devices. That has been the main focus, so to say. And we are in the final design stage of the first our chip, so we hope to have these test chips this year to show the proof of concept.
Yeah, that's great. So look forward to hearing more here. I think so. Emil and I are going to take turns in asking questions and hopefully not giving you too a hard time. So, Emil, would you like to start off?
Yeah, so it sounds very exciting. And I think generally whenever people are mentioning digital solutions, it's brought up. But what about the analog solution that we have, like phased arrays? Are these methods actually comparable, so you can compete in a good way in terms of cost and power consumption, things like that? And I think we are going to discuss these things, but let's just start saying, what are sort of the main differences at the hardware level between a analog and a digital beamforming implementation?
Yes, and if you have, I mean, the classical implementation is what we call the analog beamforming, where in the beamform you have a number of antennas, and you phase shift the transmitter receiver streams to optimize the direction of your beam. And in an analog solution, this phase shifting is done in the analog domain using analog phase shifters. And so you phase shift the received signal, say, and then you sum the signal, and then you put it to the radio and to the AD converter and go to the digital processing. And a digital solution, that's basically that you have for each antenna a transceiver chain, meaning that you don't need to have any phase shifter, since you move the phase shifting to the digital domain, where you basically then just have a complex multiplication, which is a nice feature. It's much smaller than to do it in the digital domain compared to do it in analog phase shifters. But then you need one transceiver chain per antenna, meaning that you need if you have n antenna, you need n AD and DA converters, for instance. So that's the main difference. And then you also have a much more freedom to play with the radio signal, since you have received everything, and then you can start to combine it. In the analog approach, you need to combine it. You need to have a combination, and then you combine it, and then you see, okay, this is what I get. So the digital is much more flexible as well.
So if we simplify it very much, so in a nutshell, it's like in the analog case, you need one phase shifter per antenna, but you can share one converter for the analog to digital and digital analog. And in the digital case, you don't have any phase shifters, but instead you need one converter per antenna. Is that right?
Exactly. Correct.
So how about the AD converters? I mean, my understanding has been that the AD converters are responsible for a big share of the power consumption in the receiver. So how will the AD conversion differ between, an analog solution and the digital beamforming solution?
Yeah, that's correct, that the AD converter is a power-consuming component, and that's the more bits you use, the higher is the power consumption. I mean, it's go like exponential with the number of bits. But there is a nice feature.
So I mean, do we need the same number of bits for the analog solution as for the digital solution?
Yeah, that's the nice part here. Since you have a transceiver chain per antenna, and the converter per antenna, meaning that the distortion introduced in the converter, the quantization noise, can be suppressed. I mean, then it will be different quantization noise for different antennas, meaning that you can see it as some kind of white noise, basically. And that means that if you combine the signal after the quantization, you can get some quantization noise suppression, comparing to in the analog domain, where you have a single ADC and DAC. In that case, the quantization noise you will have one single quantization noise for all antennas. So you don't have any processing gain of this quantization noise. So using a digital design, a digital beamforming or massive MIMO architecture, you can reduce the numbers of bits actually and get the same performance with respect to the quantization noise. And just to take an example, if you have an 8 antenna receiver, where you can reduce the numbers of bits with 1.5 roughly in a digital design compared to the analog. So that means that you need, of course, you need 8 AD converters compared to 1, but on the other side you reduce the number of bits with 1.5, maybe 2 if you have a careful design. So that is one advantage with digital beamforming architecture, that you don't need so many bits for the same performance.
So it's quite exciting. So you're suggesting that the quantization noise of the AD converters is independent from one antenna to the next. And then when you perform the beamforming, you're essentially summing up this quantization noise with the beamformer weights, and that will introduce some sort of averaging effect by which the quantization noise is reduced in aggregate. I mean, much like the thermal noise is averaged out by the beamforming, right?
Exactly. Correct.
So when I am sort of discussing digital solution with hardware people, what I often hear is that they are not that interested. Say, okay, we know how phased array works, and you come in with this digital solution, and you're gonna have, like, instead of one transceiver, you're gonna have 10 of them with 10 antennas, and that will consume 10 times more power. But look, you're never gonna get 10 times more performance out of it, maybe 4 times more performance. So it's not really worth it. So what is your take on those type of arguments?
Yeah, that's a typical argument you get from people when you're talking about analog versus digital beamforming architecture. That everyone understands that the digital is more flexible, have better performance, but people say that it's typically too high power consumption, and of course that is, I would say that was the truth for yesterday. But now, if you come into the millimeter wave, where you can integrate the antennas and the front end filters and the radio chip in the same encapsulation, you can significantly reduce the power consumption for digital architectures. And it turns out that for a handheld device where you have like 4 to 12 antennas in that ballpark, then with the current radio component technology state of the art, it's basically on par, the power consumption for an analog solution compared to a digital solution. And that seems to be quite surprising, since if you say have 8 transceivers, how can you have basically on par in the power consumption, both on the receiver side and on the transmitter side? It basically turns due to 2 facts. One is the AD and DAC converter. I mean, the converter that needs fewer bits, meaning that the converter itself will take lower power compared to a single converter on the analog domain. That is one thing. But the major thing is that the phase shifters, if you implement a phase shifter, that's basically some kind of routing on your PCB, and you need to have some switches to have different phase shift, different routing distances. You have quite some loss there. It's like 6 to 10 dB loss in a phase shifter today, in phase shifters using for handheld devices. And that means you need to have a much harder or tougher design of the power amplifier and the low noise in the transmitter side, and on the LNA, the low noise amplifier in the receiver side, since you need to compensate for these 6 to 10 dB. Meaning that the power consumption for the LNA, the receiver first amplifier, that need to be low noise and high gain, need to gain this 6 to 10 dB. And on the power amplifier side, you need to amplify a weaker signal compared to in an analog approach compared to the digital. So there you need to have a much higher front-end power consumption on the PA as well as on the LNA. And if you take all this into account, you will end up in basically the same numbers of power consumption for the transmitter and receiver for the analog and digital with current technologies. So I think that this is that the technology has come so far, and the miniaturization has come so far. So now the digital is on par with what you can do with an analog solution.
So it's great to hear this being said by someone actually working in the industry, because when I'm sort of saying it as an academic professor, they are... people in the industry are typically saying, well, yeah, we see the work that's done in academia, but academia, they ignore so many practical aspects, so we cannot really believe in what is being said there. It's never going to work in reality. And so, but it's reinforcing this point when actually there is agreement from the industry as well.
Yeah, I share the same experience. I mean, but quantitatively speaking, how large is the power consumption of a fully digital versus a fully analog for millimeter wave?
Yeah, if we take an example with 8 antennas, you, yeah, of course, it heavily depends on the output power. But if you have some output power of a PA power consumption of an 8-9 dBm, that corresponds to less than 10 milliwatts, so 8 milliwatts or something like that per PA. Then the total, if you have a perfect combination of all the signals, you will have a corresponding EIRP output power of 25 to 27 dBm, depending on the antenna gain and things like that. But that is, I would say, a typical use case. If you take that, then you can, with current design, digital solution, come in the ballpark around 500-600 milliwatt for the transmitter and 250 to 300 milliwatts for the receiver. And you can, looking at the 3GPP and there are different power classes in defined there depending on the use case of your millimeter wave device. For handheld smartphone, you can probably go up to like 33 dBm EIRP output power, and that corresponds to a PA output power of 13-14 dBm roughly, and then you are up to 1.6 watt, 1600 milliwatts or something like that. So, but a typical use case is 500-600 milliwatt, and half of that for the receiver.
Right, so about half a watt. And say again, what bandwidth was this for?
Yeah, the bandwidth in this case is the 3GPP bandwidths of 100 to 200 megahertz. Of course, you can in 3GPP also go up to 400 megahertz, and then you increase the power consumption a bit, mainly due to the converters and the filters needed to be designed for 400 milliwatts. So that will increase it slightly. But this is some kind of typical ballpark numbers, just to get some kind of feeling of power consumption.
Yeah, so in any case, we're well below a watt here. I mean, rather at half a watt, which is quite manageable, as I can understand, I mean, for most mobile applications. Now, your solutions focus entirely on millimeter wave.
Yep.
Versus, as I understand, most of the 5G deployments so far have been on lower frequencies.
Yeah. Yep.
So what is your view? I mean, what will we need, if at all, eventually millimeter wave band for?
Yeah, exactly. It's true that today the rollout of 5G today is basically on the sub 6 gigahertz. You except in US. In US, they are coming up also with a millimeter wave rollout, but that is in the first phase, I would say. If you need, I mean, you were talking about this kind of fancy use case with VR and AR use cases, for instance. If that will happen on large scale, you need hundreds. I mean, you need hundreds of megabit per second per users, and in that case, you need to go up to millimeter wave to have a capacity in the system, basically. I mean, you can have some few users using sub 6 gigahertz bands on this new 3.5 gigahertz band, for instance. But in order to have a large scale capacity, you need to use the millimeter wave band to make that happen. That is one thing, and but in fact, looking at the predictions done by large players in the area of mobile communication about how much mobile data traffic is expected to be consumed per month or per hour, per rush hour, per peak hour in the future. It turns out that if we continue to believe in that people will more and more use the video and which typically consumes a lot of data over the air. Something like in 5 years from now, 2025-ish, then there will be a capacity problem in large megacities. Megacities in hotspots like at train stations, at parks, shopping malls. So in order to solve it also for ordinary use case like mobile broadband or surfing or web browsing, whatever, you need to use millimeter wave in the future as well. So what people are thinking first is the VR, AR, really high data rate use cases. Yes, of course, we need it for that, but also for standard use cases in order to offload the sub 6 gigahertz frequency band. So that means that in a not so far future, I think that IoT will be similar to what you have in 5G today. I mean, you have the narrowband IoT and also this I don't know, the NR Lite or maybe they have changed the name on it right now. But where you have some IoT stuff with some few megabits per second, that one will most likely also be able to support millimeter wave in the future. Maybe not in the next few years, but in 5 to 10 years, I guess. So there's a need for this millimeter wave band in general.
Yeah, I agree. And I think, I mean, obviously, once the technology and the connectivity is there, applications will follow and will emerge, right? Yeah. So I think, Emil, you had some additional questions you'd like to ask.
Yeah, no, so I think this is a good thing to always remember, that the demand will not come over a day, so that is sort of like later on we will need it gradually. So even if a technology as such is something that is changing a lot, we will not see that change just from one day to the next one. So you were mentioning the US deployments are millimeter wave, and I was looking earlier about this iPhone 12 that they have there with sort of one antenna at the back side and one on the side here. So I guess it's two different phased arrays, so you don't block both of them. So what if we would use digital implementation instead? What would that mean in terms of how we can build handsets in the future?
Yeah, if you start to split these antenna arrays, I mean, if you have an analog array like 20 times 5 millimeters, that is what you can find in the 5G phones today. It's hard to put it in a crowded PCB. I mean, you have something in this form factor, and you can't put too many panels. I mean, you have one here, and then you block it. You need to have one here due to this problem with the millimeter wave that you had the problem with blocking by hand the radio signal. But if you split the array so that you can separate it on per antenna per transceiver basis, then you can put it wherever you want, basically, in the phone. And each of these chips might be 3 times 3 millimeters, for instance. So that means that you have much more freedom in the placement of the antennas. So you can use that to optimize the performance and reducing the risk for blocking all antennas. You maybe only block a single antenna with your hand, but you still have a number of them that are free. So it will change quite a bit the thinking of how you should do the antenna placement in a device, I would say.
So speaking of antenna placement, I mean, because the traditional view of antenna arrays, I suppose, has been to that one packs the antennas with half a wavelength spacing, right? Either on a linear array or in a rectangular topology, but in either case, with half a wavelength in between.
Yeah.
Now, if the antennas are spaced differently, like the way I understand your design, how would that impact the radiation pattern? And more generally, I mean, will the antenna spacing, is that an important parameter in the design?
As I mentioned, since you can put it freely, in general you can put it freely, and of course that will give quite different radiation patterns depending on how you place your transceivers. But what you now do is that you basically move this kind of beamforming from the analog domain down to the digital domain. So you can just let the computer do the optimization to see how you should scale, or how you should basically some complex value scaling of your received signal, and let the computer in the CPU in the device compute the optimal direction.
Yeah, right. So this is really the beauty of fully digital beamforming, right? I mean, Emil, I think I might be preaching to the converter here, but we've been, I think, promoting fully digital for a long time now, exactly on these grounds that a fully digital solution makes inherently, or doesn't have to make any assumption whatsoever on what the surroundings and the propagation environment looks like, and it'll just adapt the weights per antenna and then combine all the baseband data coherently in the processor, right? So that I think is really great to see that it's happening now in reality also for the millimeter wave band.
Exactly. And just to comment there, I guess that there could be quite some interesting research on optimal placement of antennas in say a handheld device, depending on the likelihood of you blocking, depending on how you hold the phone. So I guess that there is some nice research you can do here also as well, I guess.
Right, that's an interesting point indeed, and I suppose the transition here to fully digital beamforming changes the game, right? So that's a good take-home point, I think. Okay, Emil, you want to take over?
Yes, so I would just like to ask you one more question, namely something that I often get asked. So say that you have 10 antennas. How many beams can you transmit using 10 antennas? What is your response to a question like that?
That's a good question. I don't have any good answer right now, I would say. But looking from an commercial view, not from the research point of view, I say what you will do. I mean, it will heavily depend on how much processing you have in your digital processor to compute which direction you should transmit in. I mean, you need to look at the receiver side and see which is the optimal directions in the receivers for instance, if you have non-line of sight, or if you're communicating with a number of base station or something like that. You need to derive the optimal directions in the downlink, and then you mirror it to the uplink, the strongest path, and then you transmit in that and that direction. And what will happen is a trade-off between performance and complexity. So what will be sufficient for sufficient quality, user quality, is the right answer. I don't know the correct answer right now, but compared to analog, where you need to choose, I either choose to transmit in that direction or that direction. Which one should I choose? Now I can basically use two at least. So that's a very large difference. I would say go from 1 to 2, just 2, and then if you go from 2 to 4 or something, that I don't know right now.
Yeah, no, I think it's a good point that it's sort of the communication channel that is limiting us. And as soon as you have more than one antenna, you could create a superposition of any number of beams carrying different signals, but then of course the communication channel will limit us, and if you have 10 antennas on both sides, you can sort of distinguish between 10 unique beams, so you typically don't want to send more beams than you have antennas, even if you can possibly send an infinite number of different beams by dividing your power between them.
Yeah, it's just that the gains are diminishing, right? I mean, in principle, with 100 antennas, you could send 1,000 beams, but in practice, you would never want to send more than maybe, 50 or perhaps up to 100 or so, but certainly not really more, right? So, I mean, we focused the discussion here a lot on the user terminals, right? But is there anything that prevents your technological solution from being used at access points also?
I would say that since we are doing this scalable solution with a single chip per transceiver, so you can use it also for other use cases like fixed wireless access is one large use case, expected large use case in for millimeter wave. I mean, instead of fibers, you use millimeter wave, so it's some kind of fiber replacement for the last mile. Then in that case, you probably would like to have more antennas or transceivers, not 8 or 12 or 16, but maybe 32 or 64 or 128. You can basically just combine it. Okay, it will be different in the baseband processing for the optimized combining. You need to take care of that. You now have hundreds of streams instead of 8 or something like that. You can also use it for base station, I would say. Just take even more, 500. Satellite communication, non-terrestrial network, communication with drones or airplanes or also satellites, that is discussed and will be happen for millimeter wave and 5G. And in that case, you maybe need 1,000 antennas to reach something on the satellite. Maybe that is not a handheld device. There is some other devices that have that. And actually, if you go to the limit. I did some back of the envelope calculation. If you take this kind of chip that we are developing, giving a maximum output power of like 15 dBm in that ballpark, and if you take an array of that with 10,000 times 10,000 chips, then you have a 100 million antenna array. Then you can communicate with the closest exoplanets, 5 to 15 light years away. Of course, the data rate will only be 10 bits per second, and the latency might be a problem. But you can just scale this. It's a quite nice scaling you can use from IoT up to base station, and also for exo space communication.
So do you have the ADC resolution to decode the signals that comes from the other planet?
Yeah, exactly. There might be some practical limitation, but I think it's quite fun.
If someone responds,
that you have a solution that can scale from the simplest IoT to quite advanced devices by just adding more transceivers and antennas.
Yeah, that's a cool line of thought. I think, I mean, just talking of extremely large antenna arrays for communications is like music in the ears, both for Emil and myself, I think.
Exactly.
All right. Yeah. So now my question is really, I mean, why didn't this happen earlier, right? And if you had to speculate, when do you think that the market for millimeter wave technology will be dominated by fully digital solutions?
I mean, why this doesn't have earlier is, I guess, it's due to technology. I mean, you need to have a certain technology and radio components designed for this kind of solution to become a reality for practical implementation. I mean, digital beamforming, I guess, has been used for advanced radar communication in fighter jets and things like that. But then it's another cost scale and another power consumption and things like that. But it's now from basically now you can integrate this in handheld devices. And I guess again referring to some prediction of the number of antenna elements for millimeter wave, 5G millimeter wave that will be out around the world around 2028. It's in the order of 25 billion antenna elements for millimeter wave. So that is the total potential market, and of course many of them are in handheld devices, but also a number of in the base stations and the IoT devices and things like that. And so my guess is that in that range, starting from now to 2022 or something like that, when we have our first chip out on the market, and it will gradually become the design for design for millimeter wave transceivers, I guess. And 2028, that's my guess, and that is meaning that before the next generation, the 6G, I guess the millimeter wave transceivers will be digital. The majority will be digital, based on digital solutions. That's my guess.
So well within 10 years, I mean. So I mean, I think this also probably dictates what assumptions that academic research should operate under, right? What do you think, Emil?
Yeah, definitely. So I was writing this paper, Massive MIMO's Reality, What is Next, like 2 years ago, which was sort of based on that premise that, well, soon we have digital arrays everywhere. We can sort of forget about the analog and hybrid past and think about what else can we do when we have all of these transceivers around, in addition to the things that we already are envisioning to use these arrays for.
Oh, well, all right, good. Yeah, so I think we are close to wrapping up here today. Bengt, is there anything else you'd like to add for the audience?
No, I don't. I think that we went through quite a lot of good questions, and hopefully I have answered my view or our view on the future in a millimeter wave. So, and we really hope that will happen.
Yeah,
it will be nice and for many areas. And I mean, the research, as you mentioned, it might be more important to think about that. Say that the devices have much more freedom in the communication using a digital solution. Then you can improve the optimal capacity even more, I guess.
We agree. All right.
Yeah.
So then thanks, Emil. And thanks again, Bengt, for being with us today. And thanks to our viewers and listeners. And don't forget to like and subscribe us on YouTube. And see you next time.
Bye-bye.
Yeah. Thank you.